This is our introductory lesson for Chapter 3, Section 1. One of the first things we're going to do is evaluate exponential expressions. And so we want to make sure we know how to use our calculator to evaluate different powers. So the 6 problems you see right here are representative of the type of problems you'll see in my math lab. But right now, you want to run through and make sure you know how to evaluate these expressions. And so check your calculator and see if you're getting the same answers. 5 raised to the 1.2 is 6.899. 6 raised to the negative 2.3 is 0.016. And I'm rounding to 3 decimal places as they do in my math lab. 7 raised to the square root of 2 should be 15.673. E is the base of the natural logarithm. It's found above the key ln for natural logarithm. And so e raised to the 5.4 should be 221.406. E raised to the negative 1.7 would be 0.183. And finally, number 6, some calculators allow you to do a product of expressions raised to a power. So 25.3 times the quantity 2.7 raised to the 4th should be 1,344.546. If you need help with your calculator, look for the video recording that I will make for graphing calculators so that you can see how to enter this and get these answers. I will also use that video to show how to do shifting, translation, reflection, stretching, shrinking of exponential graphs on that video as well. All right. So here's our PowerPoint. An exponential function is called that because you have a base raised to a power. So it's an exponent. And the things that you have to remember is the base has to be a positive number greater than 0. It cannot be 1 because 1 raised to any power is 1. And the exponent x can be any real number. So I want to show you 2 exponential functions and what their graphs look like. The first one is y equals 2 to the x. If I input the integers from negative 2 to positive 2, 2 raised to the negative 2nd, we have to remember is 1 over 2 to the positive 2nd, or 1/4. If we change that power to negative 1, then it becomes 1 over 2 to the 1st, or 1/2. The ones with the negative exponents are a little trickier than if the input is 2 to the 0. 2 to the 0, of course, is 1. Anything to the 0 is 1. 2 to the 1st is 2, and 2 to the 2nd is 4. So if I go down below here and graph these points, negative 2, let me change the color, negative 2, 1/4 would be really low. The negative 1, 1/2 would be maybe there, 0, 1, 1, 2, and then 2, 4. You start to get the idea of what your graph's going to look like. It's going to pass through these points, and approach the x-axis, but never cross it. This is called an exponential growth graph. Now, let's try the same thing, and I want you to notice the base here that's being raised to the power x is the fraction 1/2. So if we take the fraction 1/2 and raise it to the negative second, we can actually use the reciprocal property and take the reciprocal of that base 1/2, which is 2, and say that becomes 2 to the positive second. And of course, we know that is 4. If we change that exponent to a -1, then this becomes the reciprocal of 1/2, or 2, raised to the positive 1, which, of course, is 2. 1/2 to the 0, of course, is 1. 1/2 to the positive 1 first, or positive first, is 1/2. And 1/2 raised to the positive 2, you would raise both the numerator and denominator to the second, and you get 1/4. So if we graph these points, -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4, about like that. And if I draw through those points, I get this graph that looks like this. This is called an exponential decay graph. Notice in the decay graph, it's falling from left to right, and in the growth graph, it's rising from left to right. And in my math lab, you are going to be doing some transformations on these two graphs, particularly y equals 2 to the x. And when I say transformations, you're going to have to recognize shifts in the graph up and down, right and left, reflections, stretching or shrinking. And I'm going to show you in a moment below how those transformations affect the graphs. Let me scroll down here. These will also be on my web page available to you. The first page says characteristics of exponential functions of the form f of x equals b to the x. And that could be any base. It doesn't have to just be 2 or 1/2. So here it's saying that the domain right here, let me change the color to maybe, let's see, I'll make it something that stands out, pink. The domain is -infinity to positive infinity. The range is from 0 to positive infinity. The graph, whether it be a decay graph or a growth graph, approaches the x-axis but doesn't cross it. The y-intercept, you'll notice right here, when you put in 0 as the power, you're going to have any base raised to the 0 return 1. So the y-intercept of your graph is going to be 1. As far as how you know whether you have a growth graph or a decay graph, that's based on the base. If the base is a number greater than 1, you're going to have a growth graph. If the base is a number between 0 and 1, you'll have a decay graph. That would be like a fraction 1/2 or 1/4 or a decimal 0.6. Any number between 0 and 1 is going to give you a decay graph, whether it be a decimal or a fraction. Any value greater than 1 is a growth graph. And remember, the base cannot be 1 or it would not be exponential. And it cannot be negative or it would not be exponential either. Finally, a horizontal asymptote. The x-axis, or the line y equals 0, serves as a horizontal asymptote, a line the graph approaches but does not cross. Of course, that will shift with the graph if the graph is shifted up or down. And so this last slide here talks about the various transformations that you can make with these graphs. And they're the same transformations you've seen with all other graphs, so it shouldn't really come as any real revelation to you. Vertical translation is when you add or subtract a number to the fraction. When you do that, the horizontal asymptote will shift from being the x-axis, y equals 0, to y equals 0 plus c or minus c, depending on whether the graph is shifted up or down. For horizontal translation, take a look at the plus and minus c. When it's plus c and it's the power, x raised, or b, the base raised to the x plus c, that's going to shift the graph to the left, the opposite of what you expect. Whereas the base raised to the power x minus c shifts that graph to the right. Reflections. When you have the opposite of the base raised to the x, that's going to reflect the graph over the x-axis, whereas the base raised to the opposite of x is going to reflect that graph over the y-axis. Then you have the stretching and shrinking. The value of c is really going to suggest which type of stretching or shrinking you have. You don't have to get real hung up about whether it's a stretch or a shrink, although the value of c will indicate which you have, and the placement of c will indicate whether it's going to be a vertical or horizontal stretch or shrink. So if you want to see more on the graphing, you need to watch the video, which is going to be a Google Meet video that I create to show you some of the calculator stuff and how you can compare this and use graphing technology to help you understand the various transformations. If you feel comfortable with it, you can probably go straight from here to my math lab. It all depends on you and your comfort level with transformations of graphs and graphing technology. We'll talk about this in class when I see you on Wednesday and Thursday. Hope you had a great Thanksgiving and see you soon.